Hi, everybody. Go ahead and get your notebooks out labeled, ready to go. We're going to start section 8.2. Half of it is on what we call a linear combination. Think about those two terms, linear combination of cosine and sine. In the little investigation that you just completed, we found that these two equations are 3 times cosine of theta plus 4 times sine of theta, and 5 times cosine of theta minus about 53 degrees. Just a little note about that 53 degree value. If you had trouble finding the amplitude, the theta value to go along with that high point, you can either just use your cursor and trace and find the max that way, or do second calc max and it will find this first theta value for you up here. Okay, so let's write those two equations down. So again, we have two equivalent equations here. I equals 3 times cosine of theta plus 4 times sine of theta, and equals 5 times cosine of theta minus, again, about 53.13 degrees. Both of those equations can be represented by this diagram. So let's draw our coordinate plane. We're going to pick a point D. No, let's not call it D. Let's call it P. Just pick a point P in quadrant 1. And there are two ways you could travel to get to point P. You could either, option 1, travel in these horizontal and vertical directions. In this case, we're going to say that that is equivalent to, it's a little bit off of scale here, 3 units to the right, up 4 units. Right? So this would be point 3, 4. Or to get to that same exact point, starting from the origin, we could say rotate 53.13 degrees and travel 5 units in that direction. Now that diagram is something we're quite familiar with. We just have to figure out how do we sort of break that down into its two components and build these equations from there. Okay. All right, so let's look at, let's see, do we want to do this one? No, let's start a new one, and we'll see if we can find out kind of where this equivalent 53 degrees comes from and where this 5 comes from, given some other info. Right, so they're going to give us an equation that has the cosine and sine in it, like you saw at the beginning of that investigation. We want to rewrite it just as a single cosine displacement. So let's write this out. We're going to express this equation, y equals -8 times cosine of theta plus 3 times sine of theta as, and watch this phrase here, a single cosine with a phase displacement. So what we're looking for is this format, some number that relates to that amplitude, but we also see that's the hypotenuse, so we'll look at that piece in a second. So some number times cosine of theta, and we'll allow for a phase displacement in here. We're going to call that d. So the first thing we want to do can help us find A and D using these values that we have already. Now this, so let's write some things out here. We're going to sketch angle D with U, the U of the horizontal side of our triangle, or the horizontal length, equal to -8, and V equal to 3. Those are the coefficients of cosine and sine in that order. We know cosine and U always go together. Sine and V always go together. Our goal is to then once we have that, figure out what A and D are. And we'll label those, and then we'll figure out, how do we put all these pieces together to actually find those measures. Okay, so let's start here. -8 and 3 would put us over in quadrant 2. Something like this. And again, one way to get to this point is left up 3, or let's put our angles in standard position, D degrees, and travel A units in that direction. So now our goal is really to just use some Pythagorean theorem and some trig and try to find those missing values. So let's do, I think, the easier one first. Let's find it. Think about how you'd find A. That's just the hypotenuse of that little right triangle. Squared plus -8 squared equals A squared, or 9 plus 64 is equal to A squared. A is then the square root of 73. Our hypotenuse is always positive, so I'm going to leave the plus or minus off of there because we don't need the minus piece in this scenario. So that's our amplitude. Remember, square root of 73 is, I don't know, 8 point something, right? That's the amplitude that we're working with. Okay, we'll put that number off to the side. So that's A. Now, finding D might be easier first to find this reference angle. Let's just call this theta now, because that angle is actually in the triangle. If we can find that measure, then we can figure out how to, we just adjust to find the actual one that's in standard position. All right. So let's set up a little SOHCAHTOA problem here. We could say tangent of theta, not D, but tangent of theta, -8. Now, if we just do inverse tangent, and actually maybe let's talk about the limitations of just inverse tangent. We know that's only going to find us one solution, but I'm going to tell you right now, in this example, that solution does not match our diagram. So we want to give ourselves at least the option of adjusting that angle if necessary. So moral of the story here, let's take arctangent, not just inverse tangent. Okay. Sometimes that very first angle you get out of the calculator will be the one that we want, but we'll see as we go through this one, that does not fit the diagram. Okay, so theta is, we'll start with inverse tangent of 3 over -8, but then if needed, we'll add 180 degrees to that, as many times as we need. All right, so let's make a little note here. Well, let's get this measure. -20.56 degrees. I'm going to write the general solution for now, plus 180n. Where's -20.56 degrees? Up to the diagram here. -20.56 degrees would be right here. The angle in our triangle, because we're thinking just in terms of a triangle, that would be the measure of 20.56 degrees. But again, none of those values is what we actually want, which is D, the angle in standard position. So I'm going to make a little note here, writing this general solution and then determining if it's our diagram. We need to make sure it's in the correct quadrant. Make sure it's in the correct quadrant. Okay. So we have here, because we used arctangent, we've given ourselves options. If -20.56 was the one that we wanted, we'd be good. We'd be done. We would just use that value. But because it's not, we have the option of adding 180 degrees. All right, we need D to be in quadrant 2. -20.56 degrees is not. So we are going to add 180 just one time in this case. That will put us here. So D is equal to about, if I take that -20.56 and add 180 to it, 159.44 degrees. And let's just look at how those compare here. start here and I add 180, that's going to put me in the position of D, which is, again, the angle in standard position is always the one that we want. So that's our D value. So theta, we start by thinking, okay, let me see if I can figure out the size of the angle in that triangle. This one even gets a little more off track because it gives us the right size, but in the wrong quadrant. We just need to make this adjustment, add 180 if needed. Let's put all those pieces together. Our equation asked for here, find a single cosine with a phase displacement. It will be in this format here. We'll just keep it 73. If we can simplify that, we should. But I'd rather that answer than some approximation. Let's keep it exact if we can. So square cosine of theta minus, and then the angle that 59 degrees, so 159.44 degrees. Whoops, like that. 44 degrees. Final answer. Okay. Let's write a little general formula for finding this, switching from what we have initially as a linear combination of cosine and sine to that single cosine with the phase displacement. So let's. Okay, so this, we're going to write out again, linear combination of cosine and sine. That's what we started with. Be something like this. Let's just use b times cosine of x times sine of x. So this left-hand side is the linear combination of cosine and sine. Either one is squared, right, to the first degree. That's linear. But we're saying this can be equivalent to a single cosine with a phase displacement. So a times cosine of x minus d. I'm using x instead of theta. You could certainly write all that in terms of theta 1. But let's take it even a step further and just sort of, every problem is going to be done in a similar way in terms of how we find a and d. So let's add to this, where a is found by just doing the Pythagorean theorem. If you did it all in one step instead of a squared, we would take a square root right away. It would look like this. Flip back a previous page on your notes if you need to see that. That's really what we did to find a. That's where the square root of 73 came from. Right? So this is the hypotenuse of that reference triangle. Okay, so really don't make it any more complicated than just a little Pythagorean theorem problem. And then that d value we find by taking arctangent of our opposite over adjacent will always be, the opposite side's always going to be the vertical one, so c over b. All right, and we want to pay attention to the quadrant. Let's make a little note here. Make sure D is in the correct quadrant. That's where the diagram comes into play. It's going to be really hard to tell if you have the correct angle without drawing the diagram that fits those B and C values that you're given right away. Okay. Okay, tomorrow I'm going to give you, although we don't need all of these yet, but tomorrow we're going to have this long reference sheet of all of these different properties related to the trig functions and look at lots of different relationships to them. We can just kind of check off the first one, but you'll have this reference sheet, not something you need to memorize, something you can reference and just know when and how to use it. Okay, your next task is pull up the online book or get your copy out, and we're going to try 1 to 11 odd. My answer key is already posted, and then 23 and 25. That's all. We'll do some of these tomorrow. Thanks, everybody.